Welcome back. In this video, we'll cover some basic mathematical ideas necessary for statistical reasoning using equations, parameters, and estimates. The good news, if you don't like math, is that the equations you'll see today are mostly condensed, so they're much simpler to follow. Much like the idealized distributions we saw in the last video, you don't need to have every single case written out usually, because we can borrow notation like the subscript I that we used with the sums, the sigmas. In fact, this condensing action is part of the core mission of social statistics, that is to parsimoniously, with as simply as possible, summarize aspects of the human experience, shared or unique, in a way that can help make sense of the reality of our world, of what you might call the social facts. So let's get down to it. First, though, you may need reminding what differentiates statistics from mathematics in general. Statistics is concerned with learning about the whole from a part, generalizing from a sample, that's the part, to the population, the whole group that we're interested in. In statistical terms, we use the data in our sample to estimate the population parameters. How we do that can range from a point estimate like the mean to complex multivariate models, but they all boil down to a single master equation. That is, the outcome equals a model plus error. Let's take that equation apart piece by piece. So the left side of the equation is labeled outcome. For a summary statistic, like the average of a variable, the outcome is the variable itself. If there's more than one variable, and there usually are, it's the dependent variable, or the variable being predicted. Model is what you might call the statistical meat of the equation. It's where the complexity can potentially come in, but it doesn't have to be complex. As we'll see, even the mean is a model. It's one that's often very useful, in fact. And the last part of any model is error. It's sometimes left out of the equations you'll see in books because it's considered noise and only modeled indirectly as what's left over. But without including an error term, at least implicitly, we don't have a model. We have a deterministic function where we know the value of one or more variables exactly if we know other variables to tell us that. That is, there's an exact correspondence. Now you're back in mathematics instead of statistics. For some of you, talking in the abstract, though, won't be very helpful at all. So let's walk through one application. Since most people are familiar with the mean or the average of a variable, we'll build an equation for predicting an individual student's grade based on the mean. So the outcome is the student's grade. So we'll write that out. We'll use the I subscript to mean, just like in the sums, grade of student number I. That's equal to mean, which we'll represent by a Greek mu here, plus the error for student I. You notice the mean doesn't have an I. That's because it's constant. It's the same for each person. Now, it's important to notice that what we're actually doing, right? You might ask, wait, but isn't this different for different people? Yes, we've got that. What we're actually doing, say we have 5 students. We have a student with 60, 70, 80, 90, and 100 for their grades. We actually have a vector of grades. We have a vector for the model, one or more vectors really, and a vector for the errors. So, that would be E1, E2, E3, and we'll fill that out in a sec. If you look, the mean of 60, 70, 80, 90, and 100 is what? 80. So even though we only have one number, it's still a vector. So what do? We fill it into each of these. 80, 80, 80, 80, 80. If you're not familiar with vector notation, this is just like a column of a table, right? You can think of it the same way. So the mean of grade, in this case, is always 80. But each student has a different grade. The error term, then, we can figure out is the difference between the true value and the prediction. So we've got minus 20, minus 10, 0, 10, 20. You notice, because grade is a variable, the error differs from case to case. The only way it wouldn't differ is if it were 0 and the mean were the same. The mean was the value that every single case had. If the goal is to get the best estimate of the outcome, then a mean is the best possible point estimate. It's the best single number that gets closest and minimizes these errors. But if you notice, if you add up all the errors, what do we get? We get negative 20, negative 30, negative 20, 0. That's always going to be true. Why is that always going to be true? Because the mean is the statistical average. So if we add up all of these, we'll get the same as all of these. So the errors will be 0. For now, just note that. That'll be important later on. But also note that the mean overestimates or underestimates by a different amount for each student. That is, the error is still a variable, even if we don't consider it when we're thinking about it directly. It's there, and it's important for estimation very often. So, we could add any number of variables to the model. In our representation, if this is for the mean, say we added another variable, we said the mean, and we were also accounting for their grade on the first test. So now we have grade of student I equals, we'll put the model in brackets and leave the error there. So now we have a constant, we'll call that alpha, plus a coefficient times the value of the x variable for that case. In this case, that x variable is exam grade. So what we're saying here in this slightly more complex model is we're saying, okay, the mean didn't do a great job of estimating. It got one person right and other students right to a varying degree. But if we also knew their exam grades, we could say that there's some baseline grade that we would expect regardless of how well they did on the exam, and then for each point they got on the exam, we would expect that their grade overall in the class would be a little bit better, right? This b and beta, in this case, and alpha, those are Greek letters typically, are constants. They're the same for every case, but this is a variable. Variable, constant, constant, this is a variable, and e is a variable. We could go on adding variable after variable after variable and doing other things to the equation, but this is the basic model that underlies just about all of statistics. For now, the main point is to understand the meaning of each of the overall pieces of the equation, that is the outcome, the model, and the error, and how variables fit in, and to recognize that although alpha and beta, the constant and the coefficients, are the same for each case, the outcome, the independent variables, if there are any, and the error can and almost always do vary between cases. Remember, outcome equals model plus error. Framing each model we discuss that way will not only help you to make fancy equations to impress your friends, it will also help you to see how everything is related and builds on each other. Thanks for watching. Until next time.